All right. Seems like it's about time. Today we will be sorry. Yeah. So I guess welcome back to class. Last week we have covered I believe three sorting algorithms. Um, yeah, and this week we'll be covering well, we will no longer be covering sorting algorithms, but rather we would be looking at rather let's look at a few others rather simple sort of algorithms. The first one, well, right now I'm thinking about I have two planned, and then we'll see if we have time for the third. The first one I would like to, I guess, introduce is binary search. Sorry, that aside, before that, I'd like to provide you with the code of for insertion sort again. I believe that's the last one we left off of. Um, yeah, 1 second. Yeah. Share screen. All right. So again, here is the code for insertion sort. It's as again to remind you if you kind of forgot about it, insertion sort is when you are um having a sorted and then an unsorted portion, except that the sorted portion um is only relative sorted, and then you're inserting values depending on where it is. Well, you're inserting values from the unsorted portion into the sorted portion, and that way you're able to keep in relative order in the sorted section until the very end. All right, that being said, again, to quickly go over the code. There we go. First, we have an array of length n. I repeat through the entire array forward. I find the number I want to insert, and then I start going backwards, seeing where I should insert. And a little something that's rather in that's rather that saves some bit of efficiency is when you are overriding the numbers while saving the key. So the key, if we have this, and then we have, let's say, yeah, we have key equals 11. So we are saving this, and then we're overriding 11 with 12. And then at the end, we put 11 back in. Then same thing with 13, well, same thing with 5. 5 is saved to key, and then 13 overrides 5, 12 overrides 13, 11 overrides 12, and then lastly 5 is placed in there. Same thing with this. These 13 replace 6, like that. And then lastly 6 is inserted, and now we have sorted array. So this way it saves time with swapping. You don't have to swap it every time. Instead, it's more of basically shifting everything to the right by 1. All right, that being said, we'll move on to today's topic, which is binary search. So far now we have learned how to, I guess, create a sorted array. Let's say like that. Now let's say I want to find a number within that. So normally, let's see. if I have a sorted an array and I would like to find the number 10. All right, what are the sum of the, I want to find number 10. Let's say I want to find 9 actually. All right, so how could we do this? Let's see. The first one you might think of is, let's just loop it through, right? For class, and that's called iterative search, or just brute forcing it. Brute force is when we say that you're choosing the easiest method of easiest option possible without caring too much about the efficiency. PSBN. Now I have an int of r equals 3. Okay. Let's create a search method. Search R. Okay. Now we have search with int R as variable. So what I want over here is I want to I'll just print it. I just print out the index of it when I get it, or when I find the number I want to look for. So also I need another parameter called num or something. So num is the one I want, is the number I want to find, and then array is the array I want to look search inside of. Now I do for okay, and then I have if how about if I return it int index equals static int if num equals r I. So what I'm doing here is I'm checking if the number is the same as the current number I'm looking at. So if array in the index is the same number as the num I'm trying to look for. If it is, I'm just going to return I, and then that. Otherwise, I'll return -1, indicating that the number is not found. Okay, so should be simple enough. We could quickly run this to check if it works. All right, there we go. Index 8. I can have a little prompt index of oh, I should probably define int num because can't call it. There we go. Num is index. There we go. There we go. Index of 9 is 8. Cool. That makes sense. All right. So let's see let's think about the efficiency of this code. Right. So I have an array, and usually when we talk about time complexity, we're talking about the slowest possible situation. So so we're always assuming the worst case scenario, which in this piece of code is 10, because you start from index of 0 and you go through the very end of the array. So something else we could do. Int steps, that in steps would be the number I'm trying to the amount of steps I need to make the code to run the code. Find the actual number. Step is never initialized. Let's put it here. Steps. Find the number. There we go. All right. So basically, I added text, a message saying that 9 steps. There we go. Right. So as you can see, to find the number 9 step is taken. And if I'm trying to find the number 10, 10 steps will be taken. If I try to find the number 11, well, that doesn't exist. I should probably put that here as well, just so I could do the extra message. Right. So you see 10 steps is taken to find number 11. Same thing for finding number 12, 13, whatever number that doesn't exist within. So as you can see, the worst case scenario is 10 steps, which is the length of the array. Therefore, this method actually has an efficiency of time complexity of O of n. Complexity O of n. There you go. Because it takes n iterations to find the actual number, right? Now that's, well, it's not terrible compared to the sorting algorithms, right? Remember that the sorting algorithms are like O of n squared and stuff like that. So this one is actually not that bad. It increases proportionally to the size of the array. However, there are some simpler methods, some other methods that are possibly better. And what I wanted to introduce you to is binary search. All right. So binary search is defined as, 1 second. Make it easier for me. All right. So binary search is the searching algorithm used to kind of search through a sorted array by basically, as the name suggests, of binary, dividing the intervals by half. So because this entire thing is sorted, I know for sure that when I find number 6, number 9, or if I know that I'm looking for number 9, and then my current index is at 7. If I know it's 7, I know 9 is definitely right of 7. So I could use that knowledge to do something. Do something. Okay. So here is the simplified version. So first, you divide the array into 2. And then you find the middle index of the entire array, right? So in this case, it will be either 5 or 6, it really doesn't matter. Depends on how your algorithm runs. I don't have a preference. Okay. So let's say the middle number is 6, right? So I have number 6, and I check if 9 is larger or less than 6. If it's larger, which it is, then I'm going to look at the right side of the array, because I know the number must fall within it. Then I find the middle index of this, which is, well, happens to be 9. So voila, there we go. However, let's say we have number 3. Right, I want to find number 3. I look at number 6. Actually, number 2. There we go. I look at number 6. And okay, so 2 is less than 6. Therefore, it must be on the left side of this of the number. Therefore, I'm going to take the left portion. And then again, I'm going to find the middle number. That happens to be 3. And apparently 2 is still less than 3. Okay, so I know that the number I'm trying to find, it must be left of this current index. Therefore, let me move to the left again and select these two. Select that portion. And then I take the middle index, which happens to be 2. And there we go, found it. All right, so it is because it's the idea of using information that's already stored in the array to cut down the amount of time needed. Okay. Let's now take a little, I guess, deeper look at this. First, now we understand the basic logistics. We can have a more, I guess, pseudocode approach. First, I want to find the mid number. Middle number is going to be the beginning plus the end divided by 2. Right. Because the beginning is 0, the end is 9. I divide that by 2, and that gives me. I'm gonna put in this. Goes from 0 to 9. Right. So 0 plus 9 is 9 divided by 2. That gives me 4. Okay, so index 4 is the mid. 0, 1, 2, 3, 4. Okay, that's acceptable. Or if you want, you can add 1 or something. It doesn't really matter. I mean, like you can round up instead of round down, but yeah, that doesn't really affect the code. Okay, so I first find mid, and then I check if mid is equal to the number I'm trying to find, right? Because it is completely possible that the number I'm trying to find is 5, and 5 happens to be the mid number. So if a mid is equal to number, then I'm done, right? If mid is larger than num, then I know that the number must be less than mid, and therefore it's going to be along the left side. So the end will be, now I have to update the end, and the end will be the mid index. Okay, well, I can't use mid here, mid val, there we go. So mid val represents the middle value, and mid represents the index. So n equals mid minus 1. Okay. However, if mid val is less than num, then the beginning must be, so that means it must be on the right side of it, right? So now the beginning is 6. The entire section I'm looking for, beginning is now 6. Versus if it's less than over here, then the beginning doesn't change, the end changes. So now it's beginning equals mid plus 1. Right, okay. Now let's take a look at, now let's take a look at how we would approach next one. All right, so now I have 5. All right, let's say I want to find the number. Okay, find number 2, this logic works, right? However, if I want to find number 9, the calculation for mid no longer stands. Now you have to add a beginning to it, because that way you can find the mid value over here, and then you add the beginning portion to it. If you want to try this, if you want to double check this yourself, go ahead, feel free. However, I'm gonna put this statement out. I'm gonna just conclude. I'm gonna summarize it for you, and that would be how the equation works. All right, that being said, let's take a look at how you could possibly implement this. Okay. Make it a small. Okay, so we still have the two arrays. We have an int beginning, int end, right? Because these are the indices. Array dot length -1, so so it can stay within the boundaries. All right, and now let's look at while loop. Let's have a while loop because this code would run forever until it no longer stands. When would it not stand? Okay, so here is I guess here is the other thing. When does it end? The ending condition is, let's say we narrow it down to number 2. What happens then? That means the beginning is the same as the end. Or if number doesn't exist, let's say I'm trying to find number 2 over here, and 2 doesn't exist, right? This is the mid value for the first part, and then so 6 is the mid value. Then it's going to check this side. It's going to check 3, and 3 is still less. So now now it's going to check 1. However, beginning and end would overlap. Therefore, because beginning must always be less than end, as long as it's greater than end, that means that this code has reached the end. Reached the final has finished basically. Right. Wait, no, this doesn't. Okay, so while I guess beginning is still less than or equal to end, that means like this code still continues to run. Otherwise, otherwise you know that it's gonna be -1 because return -1 because you know that now beginning and the end has overlapped each other, and then that means the number you're looking for doesn't exist. I'm going to change this to 11 and remove number 3. So shipping. There we go. So I have some numbers within I could test for. Okay. Now I'm gonna check. Well, now I need to find the number mid, right? Int mid equals beginning plus beginning plus end divided by 2. Right. Oh, sorry. One more step. Because I need to remember how many steps I've taken to see the efficiency of the code. Step plus. Cool. Okay, so now let's go into our check if conditions. So if array mid is the same as the num, which is the number we're trying to look for that, return f. Else if else if what's our next condition? If mid is larger than num, array mid is larger than or equal to larger than num. Then I need to update it, right? So beginning equals mid plus 1. Else, then that just means that it's going to be less, right? If it's less, then Oh, my bad. So it should be end equals mid minus 1 because it's on the left side. Else, beginning equals mid plus 1 because it's on the right side. All right, so that's actually it for the code. Yeah. Okay, I'm gonna get this print statement out over here just so we know how many steps we took. I'm not sure why it's loading. Okay. All right, gonna move it here. Then steps, I'm gonna make that a, there we go. Okay, cool. So that way I don't have to have so many if statements. See if it works. Should return -1 because number 2 doesn't 10 doesn't exist. Ooh. Don't know why that's taking forever. Seems like it's in that. Me print out the mid. I'm not sure which is there. Mid. Yeah. I'm gonna sign mid every time. All right, it seems like it found it, but it doesn't exit out. All right. Stuck at 4. Let's see why. Stuck at this. So first we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Better look at just make life a little easier for myself. All right, so first it goes into 25. Oh, so it's stuck at 25. That's odd. Gonna debug this. See some it's possible error. No. Seems like sorry, computer's a little laggy today. There we go. Set a breakpoint over here. All right, so let's see what's going on. So beginning is 0, ending is 8. That's all great. Okay. Mid, let's see. Mid gives us 5. That makes sense, right? Because we're looking for the mid should be, get this out. Right, mid is 25. That makes sense because it's length 8. All right, so I'm checking the numbers, which of course it's not equal. And then array mid should give me 25. 25 is larger than num, therefore it's on the left side. Therefore, it should probably give me a new end. Okay, so now end is 3. And then you should get rid of the else statement. That's all good. Cool. Now step +1, because why not? We're checking for mid again. Because mid is between 0 and 3, it's gonna give us 1. There we go. Yes, it's gonna give us 1. Okay, so it's checking if it's cool. It's not. It's checking if it's greater. It's not. So therefore, beginning is now mid +1. So because it knows it's not in this source portion, so it must be between 2 and 3. So now 2 plus 3 is 5 divided by 2. That gives me 2. 2 plus 2. Oh, I think I see the issue. Right. Okay. Okay, yeah. So here is the issue. So this if statement, that would give me 2 plus 3, which gives me 5. 5 divided by 2, so because I'm trying to find the number that's within between them. So 2 and 3, that would give me what is it? Sorry, 2 and 3, that gives 5 divided by 2, that's 2. So 2 plus 2. So not so good. This one should be n minus beginning. There you go. Because well, I'm trying to find difference between them, find the sum, and then plus beginning. So I'm sure there's another way of doing this, but yeah. Sorry about that. Now if I run the code, it should give me, yeah, okay. It took me 4 steps to conclude that the index of 10 is -1. It doesn't exist. Now let's try to find any number that works, right? Maybe 81, let's say. Whoa, look at that. Found it in another 4 steps. Okay, so here it is. That's the first approach to binary search. You look for the middle of the term, and then you repeatedly search for it. I'm going to get rid of these. Okay. Yes, sorry. I repeatedly look for the beginning, middle of the number and check if it's greater or less than. If it is, then I'm going to move it. I'm going to move the range I'm looking for to a smaller portion. So yeah, this code should be simple enough. So if you wish to try to code this yourself, I'm going to get rid of this, get rid of that. And then, okay, so here is your driver code. I'm going to give about, all right, I'll meet you at 6. I mean, or like in 20 minutes. And then that would include both a break and the time for you to finish the code. Sorry, actually, 55, because I still have one more greedy algorithm I want to cover. So come back at 55, try this code yourself. After you finished, go take a break, and then I'll see you in 15 minutes. Sorry, as always, I'll be available through chat or just talk to me. Either way, I'll be available to answer any questions. If not, go take the break and finish the code. All right. So it's 55. So, and we will move on to our next part, which is greedy algorithms. Before that, I'd like to show you the code again in case anyone have any questions. Okay, so that'll be it. Uh, if anyone have any questions, again, feel free to ask after class or email me. With that being said, we'll move on to greedy algorithms. Greedy algorithms is a rather broad sense. It's not a certain algorithm per se, but it's more of an approach. So greedy algorithm is basically creating a solution to the problem by always making the best choice at the moment. So without considering the future possibilities. So, and again, a greedy algorithm never takes back its choice. So whatever you choose right now would be the part of the final solution. And it is for that reason usually extremely efficient because you don't have to go back and revise. However, the difficulty in designing such algorithm is to find a strategy that always produces an optimal solution to the problem. So that is the locally or like the optimal solution at the time in a greedy algorithm must always be the most optimal solution overall. And it is sometimes rather hard to argue that whether a greedy algorithm works or not. So it's mostly a lot of times based on your intuitive sense rather than some sort of mathematical or computational proof. All right. So a first example I'd like to talk about is um, given a set of coins. So I have, I'm going to put it here, greedy Q1. Given a set of coins, so these would be the US coins. So let's say, um, let's see, 1, 5, 10, 25, 50, yeah, and then 100. These are in cents, of course. All right, and then each coin can be used as many times as you wish. And I want to use the least amount of coins to to get a sum, to form a sum of money, denoted by N, let's say. That is N dollars. Sorry. And then, okay, so this is first question. How can we approach it, right? Let's say, and well, let's do some analysis, right? First, let's say N is 75. Uh, let's do it bigger. N equals 264. There we go. It's of course it's in cents. Right. Yeah. Um, how can we approach it, right? So the optimal solution for this one is 100, 200s, and then 150, And then lastly, a dime, and then for 1 cent. Right. How did I get this? Well, so this is actually the optimal solution of this code. So this simple, so this is the simplest form of greedy algorithms, let's say, and it is always to select the largest possible coins until the sum of money has been reached. Because so okay, so how do we know if it always works? So it is. Let's consider. Okay. So it's really so it's okay. I guess it's rather hard to argue this configuration would be the easiest way. How will be the most optimal way, but again, intuitively, it makes sense. Why? Because it is because you're always choosing the largest possible value first. That means that you're always the goal of which is to save up for the or to always get rid of the largest amount of sum, add the largest amount of sum possible until you can. So it turns out, for at least for or for these kind of coins, it's pretty, it is going to be the optimal solution because as long as you have more than one copy of the same coin, so let's say like if we have 2 copies of 25, you could replace it with a 50 for sure. If you have 2 50s, you could be replaced by 100 for sure. Um, yeah. So that way, in these cases, let's see. Also, that it cannot have 4 ones, 5 ones because 5 exists. You cannot have 10, a 10, 2 tens and a 5 because 25 exists. So there's always some sort of more optimal solution for this kind of code. There's always a more optimal set possible if you don't follow this kind of approach. So greedy algorithm is less about the type writing the code itself. So I'm gonna be a little more brief on it. I'll still write it because I believe this is many people's first introduction to algorithms in general and maybe Java at all. So I'll try to keep it like that. Okay. Let's call greedy driver. So this is a driver code for the greedy algorithm. Public static void. Driver just means the code that runs something. Right? Driver. There's nothing to input. So now we have int coins equal actually seeing how much time we have left, I'm gonna leave this algorithm for like practice and then we'll move on to the second part of the greedy because there's quite a bit of stuff related to I guess greedy algorithm in general. All right, so let's take a look at some possible scheduling problems. So many problems related to like making a schedule or scheduling something can be solved by a greedy algorithm. So given I guess greedy number 2, given some event, given I guess n events with starting and ending time, right? And you're supposed to find a schedule that includes the most events possible. And you cannot, you have to attend the entire event. And event must be attended. All right, so let's have a let's have 4 events. So A, B, C, B, and then event, this will be the start to it. This will be the end to it. So start, and then, I don't know, just start to maybe 3, 6, then 5, 9, 8. Cool, should be fine. All right. So over here, the actual possible max event is 2, because, well, we can select B and D, or yeah, we can only select B and D, or I guess A and C if you really want to say it. All right. A, B, C, D. 1, 2, 3. And B starts 2, 3, 4, 5. C starts from 3, 4, 5, 6, 7, 8, 9. D starts from 6, 7, 8. There we go. So that is how ABCD runs on the timeline. Each minute, each hour or minute is represented by its numbers. So I'm gonna tell you that it's possible to use 3D algorithm on this, and there's actually several greedy algorithms you could probably get form from this problem, but we need to know which one actually works. So the number one, algorithm 1 would be, all right, let's find the shortest events possible. Let's say, so let's find the shortest event possible. So in this case, it's going to be 1 and 3. Seems like it works, right? However, if B and D are to switch place, right? So if B is now 2 and D is like that, this is no longer the best case, because otherwise you would have just had 1. So, or let's say like, think in another way. Okay, let's say this is like this, right? So if we selected B and D, we're giving up the possibility of A and C and maybe some other future events. So this makes it not possible to select these 2 long events that might have been, or like if D doesn't exist, and then have this, right? Now, if we selected B, we wouldn't be able to, if we selected B, we wouldn't be able to select A and C, which although are longer, but they do not overlap. Therefore, we can get 2 events instead of 3 events in here. Doesn't work quite well. All right. So shortest events. Not possible when, let's say like, use X. X. And then we have like X. X. Therefore, we ignore the 2 long versions. Okay, so maybe algorithm 2. So let's always select the next possible event that begins as early as possible. So I'm trying to shorten the time available between the 2 events. Right. So in that case, I will be selecting A and C because A ends at 3, C starts at 3. So they can connect seamlessly, right? However, this wouldn't work if we have this case. Right. If I've chosen the first line, I wouldn't be able to have 2 events instead of 1 event. So so algorithm 2 only selects 1 event, while it is possible to select the other 2 events instead. All right, so let's take a look at algorithm 3. What else have we not covered? Let's see. as you might have guessed, this is the correct solution. So it is to find the events. Sorry, I'm gonna make a note. Event that starts the earliest. And fails when find the event that ends the earliest. Right. So in this case, it would be A and then D because B, of course, is covered by A. And turns out this is the optimal solution. It is actually always the optimal solution, and that is because that is for this, that it is always the best to first select an event that ends as early as possible, and then it's still the optimal choice to select the next event using the same strategy until no more events can be selected. Let's see if okay. So I guess a way that you could argue that it's best because we could think about what happens if we first select an event that ends later than the event that ends earlier, right? So now we would have at most the same number of choices as how we selected the next event. So selecting an event that ends later would not give any better solutions. Thus, I guess greedy algorithm exists because as early as if the event ends the earliest, that means I have more options or available time to choose from the rest of the remaining time. Versus if I end an event later, that have less free time to choose whatever other times I have. Oh, that was a mouthful. Okay. So that will be it for second greedy algorithm. These code are not necessarily hard to implement. It's just I don't see. I think the value in them are not as great as I guess going through the code of other algorithms like insertion, iterative, or binary. So instead, I will be going more over some sample problems that you commonly see. So you're more aware of the logistics because the code itself isn't terrible. All right, so greedy. We probably have time for this is time for the last one. Maybe we'll have one more. 2, 3. Hmm, hmm. Um, Here we go. There we go. 3D Q3. Let's say sorry, so I'm trying to think. Let's consider this problem. So we are given again and tasks with durations and deadlines. So you have to complete the task before the deadline in order to finish it, right? So for each task, we're trying to earn points, right? Earn d minus x points when d is deadline and x is moment we finish. So we're trying to finish as early as possible, basically. So in order to maximize the points. So let's say we have this task duration deadline. A, B, C, D, duration of 4. Say that. There we go. All right. So what do you think is the optimal solution, actually? 0, 2, 3, 0, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Should be enough, right? Yeah. Yeah. So we have C. Yeah, we start with C. C goes lasts for, I believe, 2 minutes. So C lasts for 2 minutes, and then B, which lasts for 3 minutes, and then this isn't a very good way of marking it. Sorry, let me think. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. Yeah. Assume this is the timeline. We have C that lasts for 2 minutes. Then we have B that lasts for 3 minutes. And then we have A that lasts for all the way to 9. And last we have D that lasts for the remaining of the time. Right, so this turns out to be the most optimal solution. So in this solution, C gives 5 points. B gives 0 points because B ended at when it should have ended. A actually gives -7 points because it ended later than it should have. And then lastly, D gives -8 points. So totaling -10 points. So it turns out this is the best solution. And how you determine that? Well, actually, we can kind of guess how we found the best optimal solution. And actually, it is not to consider the deadline at all. It is, in fact, the actual correct way of doing this greedy strategy is to just do the tasks by sorting their durations in increasing order. So you do the shortest task first, and then you move on to the longer ones. And the reason is that if we perform 2 tasks like one after another, so that the first task takes longer than the second, we can always get a better result by swapping them, right? So if I have C and B, I get 5 points from doing CB. However, if I do BC, I would get definitely less points, right? So that means as long as the task longer task before, shorter task gives less points than swapping them. Right. So therefore, it's always best to the conclusion is for any consecutive tasks, you must shorter task must be completed first. Therefore, when you take that into the consideration of the entire row, you just get a sorted array of from the lowest number to the largest, and that gives you the best performance. All right. We have time for one more, I believe. Yeah. All right. So now hmm, let's consider trying. So let me think. Okay. I'm gonna introduce something that's that's like an extension of greedy because I believe there's still a few other greedy algorithms, greedy algorithms such as data compression or minimizing sum. However, they get a little more complicated, and I don't believe they contribute greatly to our course. So I'm gonna skip them, and then let's take a look at what's called Huffman coding. So Huffman coding is, I'll spell it out. So Huffman coding is a greedy algorithm that creates an optimal code for compressing a given string. So it's like data compression. And makes use of greedy. So this is a real life application of greedy algorithms. So it creates a sort of a binary tree. I should probably, forget about it. I'm going to talk about binary trees first because that is quite an important topic of algorithms. So binary Java. All right. So binary tree, as the name suggests, is so let's first talk about what's a tree. So tree is a list of nodes connected by paths, or like a list of connected nodes. So an example of which would be, it's a little hard to draw. So let's say 1 and 1, 6, 5, 4, 6, 7, and then they're connected like that. To number 5, right? Um, so see if I can draw because I believe that would be a little better. This will be quick. Actually, forget about it. So number 5. So this is a little not so good of a demonstration, but you could probably imagine that you have like a few nodes, then they are connected to I guess a parent or a node that's above all the other nodes. Um, so the reason why I want to talk about this is the binary tree is a rather special kind of trees. So a tree is made of nodes, not nodes. And nodes are just a point that's not store some values. So we have 5, let's say we have 5, and then 5 is divided into like 3, 4, and maybe like 3 is then again divided into, I don't know, like 1 and 2. Right. So let's say this is a binary tree, right? So so this is what's called a tree. This is what's the root of the tree because it's the very beginning of a tree. And all right, I can share a whiteboard. There we go. Or not, because apparently it's my computer doesn't like sharing whiteboards. Okay, you know what? Forget about it. I'll talk about binary trees next class. And today's homework would just be implement, I guess, the coins problem that we have talked about earlier. So the coins are 1 cent, 5 cent, 10 cents, 25 cents, 50 cents, and then 100 cents. So you're trying to, I guess, create some the thing that I talked about, which is trying to find the largest, trying to find form some sort of sum with those coins, and by using the least amount of it. Or if you want to do the other two, it's also fine. It's just a bit of practice for coding and nothing else. That being said, next class we'll be covering binary trees, binary index trees, probably Huffman coding, and then a few other things. We'll be looking at a few actual contest problems from USA Computing Computing Olympiad, which is a I guess computer algorithm competition that you can participate in. I'll show you a few problems from the entry level which is bronze division, and then yeah, we could start from there. That being said, feel free to. That's it for today. So if you want to, feel free to leave, and I'll see you in a few days. Have a great week, and as always, I'll be here for a few minutes to answer any questions.